Hi, this is Albert van Dijk, and in this video I'd like to explain a little bit about satellites and orbits. Now, this is not an aeronautics course or anything like that, so I'm not going to get in too much detail, but when you look at remote sensing imagery, you've got to know a little bit about the orbit of the satellite, and particularly you've got to know whether you're looking at data from a geostationary satellite or from a polar orbiting satellite. So in this little diagram, you see the main difference between the polar orbiting satellite here, which is going around the Earth in circles at an altitude of about 850 kilometers above the surface. And on the other hand, here we see the geostationary satellite, which is looking at the whole disk, as we say, the whole Earth, as much as you can see it from one side, and is always looking at the same spot. So if it hovers over the US in this case, or that side of the Earth, the Western Hemisphere, it always hovers over that exact same spot. And to do that, it has to be at an altitude of about 36,000 kilometers above the Earth's surface. So why is that? All right. To look at why that might be, we need to sort of understand a little bit about the forces that act on the satellite. I'm going to try to keep it pretty simple. But one thing that you'll realize is to always look at the same part of the Earth. The satellite has to go around in a full circle the same time it takes that particular place on the Earth, and of course that will be a day. So one thing that is certain is that the satellite needs to have a period, as we call it, make a full circle in one day. And if you know that, then you can also work out at what altitude it needs to be to achieve that. And to do that, we can use the formula for centripetal acceleration, which I'm not going to derive here, but we're going to apply it. If you want to see the derivation, you can look it up on Wikipedia or whatever, and there's a good explanation of it. What is important for this formula is that the velocity of the satellite, so that's v, and the radius of the orbit are in balance by the attracting force or the gravitational force of the Earth. And the gravitational force of the Earth is given by the mass of the Earth times the gravitational constant. Now, if you put that in the formula, and we rearrange the centripetal acceleration formula a little bit, then we can write it like this, where we say the velocity of the satellite has to equal this term here, the square root of gravitational constant times mass divided by radius of the orbit. But of course, what we also know is, as we said before, the satellite has to go around in one day, and so we can use that knowledge, and we call that t, one day, and we say the circumference of the orbit, 2 pi times r, divided by the period t, is equal to the velocity. So we've already rewritten it into this way. We've got rid of v, and now we can try and solve it. And as you'll realize, the gravitational constant is a constant, the mass of the Earth is known, the period we know as well, it's one day, and so all we need to know out of this formula is r. And so we're going to reshuffle the formula to get r on the one end of the equal sign and the rest on the other, which is what that looks like. And if you know that, if you got that, then you can, of course, you can fill it out. So we fill it out, we put here the number of seconds in one day, you can calculate that, that's come back to that, the gravitational constant, and the mass of the Earth. As you can see, the Earth is quite heavy. And we divide that by 4 pi squared. So if you do that all in your calculator, then you ought to be getting this answer, 42,300 kilometers. Now, that is not quite the same as the number you saw before, and that's because what we saw before is the altitude above the Earth's surface. So I have to subtract the distance from the Earth's center to the surface from the total orbit radius to get the altitude. And the Earth's radius is 6,380 kilometers. We know that. And if obviously, I'm not saying you know that from the top of your head, but you can look it up. People have measured it. And then we can calculate the altitude as a difference between those two, and there's your more or less 36,000 kilometers. So this is the only way that a satellite can be in a geostationary orbit, moving at the same velocity around the circle as the Earth's surface does, and therefore looking at the same spot and be in a equilibrium, if you like, or near an equilibrium with the Earth's gravitational pull. So what's the advantage of a geostationary orbit? Well, the biggest advantage is you see half of the Earth, as you can see in this diagram here. And you can therefore continuously look at it, so you can see it at very high temporal resolution in the order of minutes, however long it takes you to scan the whole Earth, basically. And that's really useful, as you can imagine, particularly for things like weather forecasting and whatnot. The disadvantage is that because it's much further away than a polar orbiting satellite, it's a bit too far to get really high resolution imagery. So typically it's more than 1 kilometer, and also you're going to get distortion at the poles. So if you're particularly interested at the poles, then a geostationary satellite is probably not the most useful way to go. So here's a picture or a sequence of images from a geostationary satellite MTSat, which is the precursor of Himawari 8 that I talked about in a previous video. A geostationary satellite that looks at Australia, among others, the whole eastern hemisphere. So what you see here is Cyclone Ita in 2014 approaching the coast. And so the only way that you can get this sort of detailed temporal information is with the geostationary satellite. Now, as I said, we've got Himawari 8 now, again, a Japanese satellite, and it's worth your while having a look at this link here. Of course, you can't click on it, but you can copy it into your browser and have a look at some of the most recent imagery for Australia. It's quite fantastic. This Himawari 8 is a major improvement compared to this previous MTSat. All right, so that was a geostationary orbit. Now the polar orbit. So the characteristic of a polar orbit is that it always passes the equator at the same time. And particularly, it usually passes the equator with the sun in its back. And we call that sun synchronous. So to achieve that, we can do that in about 100 minutes velocity, orbit velocity, and that will take you about 850 kilometers above the Earth. And you can use the formula that you saw before to calculate that. If you put that 100 minutes in there instead of a full day, then your answer should be about 850 kilometers. Now, polar orbit has an ascending track, as you can see here, is going northwards, and then it's got a descending track. The other end is going down again. And so when you map that to a projection like this, you'll see these sort of swath patterns, and you'll also realize that one of the two can have a daytime crossing, and the other one's going to have a nighttime crossing. The two will be 12 hours apart. Here's another example of a polar orbit designed to have a 7:30 equatorial crossing descending and a 7:30 evening ascending crossing. So as you can see in this case, they go across the equator more or less dusk and dawn. You see the same here from one of the poles, and you see inevitably the poles get a lot of coverage, and the rest of the Earth, particularly around the equator, you get the least coverage. So here's what the Landsat 8, the current Landsat mission, sees in one day. And as you can see, there's all the swaths here, and it can only look at a fraction of the total Earth surface, and that is because it images a quite high spatial resolution, which inevitably brings with it the necessity to not look quite as wide a swath because of the sensor limitations. Here's another way of looking at that, and if you look at the MODIS satellite, which has much broader swaths and lower spatial resolution, you see that it can almost cover the whole Earth in one day, with except the equator, it skips a little bit every day. So this is a relationship between track swath and resolution.